Hello everyone, Yuriy Reznik here from Brightcove, and today I'll talk about performance analysis of low-latency DASH and low-latency HLS streaming systems. And the talk will have a few parts. First, I'll try to introduce overall context and objectives that we set to ourselves in conducting this work. Then I'll talk about evaluation frameworks that we put together to study these types of streaming systems. Then I'll bring results. And at the end, I'll try to drive some conclusions. So with this, let us try to take a look at overall context. As we all know, streaming delivery over the internet today is done by means of HTTP-based streaming protocols. HLS and DASH represent two dominant families of such protocols and standards. And traditionally, these protocols been working reliably, scalably, but they've been operating with considerable delays. 10 to 30 seconds delays were quite typical for traditional HLS and DASH streaming systems. Recently, in order to try to reduce delays, there have been several modifications done to the standards. There is extensions of DASH as well as CMAF standards, producing low latency or ultra low latency, as some of them called, profiles. And also there is a low latency HLS that's been produced as a standard by Apple about a couple of years ago, and there is now a set of reference tools, test streams, and also client implementations available to put those standards to use. But and of course there have been lots of demos and lots of interest around these protocols in recent couple of years. But the question is, how good this new low latency variants of HLS and DASH really work when we put them to serious tests, when we operate these clients under pretty challenging network conditions and realistic network conditions. And with, for example, wireless networks with considerable loads or handoffs and other typical situation that may happen in practice. So to answer these questions, we decided to conduct a study. And of course, a related question that we're hoping to answer is that try to look at the population of different implementations of streaming clients available for each of these standards and see which one are more robust. Also, try to understand, are there any trade-offs that are essential for the systems? If lowering delay is gratis, or it really comes at the effects of some other key factors that needs to be understood and considered. So with this being a whole set of objectives, let us now talk about evaluation framework. So to evaluate both HLS, low latency HLS and low latency DASH systems, we built a complete system setup, starting with source of video, encoders, packagers, origin servers, network simulator that was producing consistent network behavior in all tests, and also streaming clients with engineered analytic collections on top of it, and run those systems multiple times to collect statistics. And to build the system for low latency HLS streaming, we used FFmpeg as encoder, and we used Apple reference HLS tools that provide low latency packagers and other tools needed to build such systems. And for low latency DASH, we used also FFmpeg and Node GPAC DASH as components for content generation. A couple of references below provide additional details. And as clients for low latency HLS, we used Apple's native AVPlayer framework, as well as HLS.js and Shaka Players. which are varieties of JavaScript-based clients. And for low latency Dash as clients, we used Dash.js, including two variants, so-called L2L, L2All and LOL algorithms, which are machine learning-based ABR selection algorithms that's been proposed last year at ACM Multimedia. The couple of papers that we list here at the bottom provide exact references. And so in design of the systems, we really try to ensure that for both low latency HLS and low latency Dash, we build systems as consistent as possible and as identical as possible as far as content preparation and network simulation is concerned, to make sure that we're comparing apples to apples. And specifically, what we used for network simulator was Mahi network simulator, which is a high accuracy, low level simulator that can reproduce network behavior based on pre-recorded traces of physical networks measured in field. Specific traces that we used were recorded traces of behavior of Verizon for GLTE network as well as T-Mobile for GLTE network. Both of these traces are pretty challenging. Right in the middle of the session, there is a handoff situation where the bandwidth drops almost to zero. And for our purposes, this is just perfect. We want to force clients to buffer at least once and see full spectrum of behaviors of streaming clients and streaming systems. And if you look at average bit rates achieved by this traces, it's also not that great. On average, it's only 1.6 megabits for T-Mobile, 1.3 megabits for Verizon. Of course, if you look at spikes, the spikes could go to tens of megabits as we commonly observe in practice. But if you look at average behavior, it's actually lower. And if you look at particular spots, these traces do have some very serious difficult spots where we do expect clients to buffer. Challenging traces, but this is precisely why we do the study, and this is precisely what we want to observe. We want to see clients being robust and be able to operate even when networks is as difficult as these are. And to send content over these networks, we created an encoding profile with maximum bit rate, importantly set at a level below the average bit rate. It's 1.2 megabits, and at the lower end, we encoded to about 279 kilobits. So we do cover the dynamic range of the network by this profile. All streams encoded using CBR encoding. There is no extra possible negative effects that could be introduced by VBR nature of the content. Big Bug Bunny is used as test sequence. And importantly, it is looped, and the duration of streaming systems that we used was about 10 minutes. 10 minutes is long enough time to be able to observe varieties of changes in client states and their adaptations to different dynamics of network, and build statistics that are sufficient for study. And with this, let us now talk about test results. And first, I will present results for Verizon for GLTE network, and then for T-Mobile network. On the left, I will be showing results obtained for low latency HLS clients and systems, and on the right side, I will be showing results presented for low latency Dash. And what we see first, we see that in both cases, throughout our sessions, the clients were switching a lot. We see that, for instance, close to the end of the session, AVPlayer was switching almost on every segment. It's pretty densely filled region down there. But luckily, it was staying close to the top rendition for most of the time. Some other clients were sticking to the lowest rendition. So some clients, in particular in this case, it's HLS.js for HLS-based systems, was not using bandwidth to full extent. Other clients were. Similarly, for Dash, we see that some clients also didn't use the full bandwidth. For example, Dash.js with LL algorithm was consistently sticking to the lowest bitrate renditions, while others were able to pull more bits. So quite a different behavior based on player implementations. But then what is also interesting is the variation of latencies that we have observed with the system. And this is where the difference between client implementation manifests itself even more further. For instance, for HLS, low latency HLS, we could see that some clients have pretty advanced logic when they try to stay at a low latency regime as long as they could, but if they couldn't, for example, because of drop in network condition or some other characteristics that tells them that they cannot sustain it, they fall back to longer latency points. So, for example, AVPlayer, through first half of the session was trying honestly to operate at sub 6 seconds. But then in the middle, when we had this handoff situation, it switched to about 12-second delay, and then closer to the end of the session, it went all the way up to 18 seconds. So quite interesting dynamic behavior and logic that Apple implemented in this design of this player. Other players were more straightforward. They tried to stay to the constant lowest latency throughout, and actually Shaka Player was more successful. HLS.js, as we could see, have lots of spikes. It tries to stay at lower latency, but it just buffered a lot, and that also caused it to increase latency in many cases. In terms of variability of latency latency for low latency Dash players, it's much lower. In fact, all players seems to behave quite consistently. They all deliver close to 3 or even less second delay for majority of the session, except for a couple of spikes in the middle, which I suspect are periods where they run into buffering. So this is a snapshot of dynamics that we observed, and these are summary statistics. And in addition to a couple of metrics I just shown, we actually measured metrics for about 7 different parameters. We looked at average bitrate, average pixel count in terms of, for example, video height as delivered, average latency, variation of playback speed, number of switches, number of rebuffering events, total number of amount of data downloaded, total amount requests to download data have been made. For instance, chunks and segments, different systems, they pulled by different mechanisms. And what we observed is that, for example, HLS, low latency HLS does make many more requests to download objects as opposed to low latency Dash. But one grand observation that could certainly be made is that both LL-DASH and LL-HLS system do seem to buffer and switch a lot in this test, but some players were much more robust, and particularly among HLS players, AVPlayers has shown to be most robust. By far, it switched buffered only once, and that's precisely what we could expect because of handoff situation in the middle. Similarly, among Dash players, Dash.js was most robust. It also buffered single time. Other players were buffering 60 times or more. This T-Mobile results are pretty consistent with what we've seen before, but remind you, T-Mobile trace that was captured here uses a slightly higher overall bitrate, and that seemed helped in reducing variation in latency. For instance, for low latency Dash players, we now see that they all stay pretty consistently below 3 seconds, and there is no spikes anymore. So slightly better network does help. And what we also notice is that variation in latency for HLS, low latency HLS players, is also much lower. So AVPlayer still switches to longer latency regime close to the end of the session, but it switches once, not twice, and in in the highest regime, it still operates at lower latencies as opposed to previous case. So, but other effects are the same. Still lots of switches, still lots of bufferings. AVPlayer is still most robust for low latency HLS, and DASH.js is still most robust for low latency DASH players. Same effects in terms of number of objects pooled, same effects in terms of abilities of different players to stay at lower latency. Now, what can we say based on this study overall? Well, good news is that both low latency HLS and low latency DASH systems seems operational. You could build such systems today. And if the objective is to deliver streaming with end-to-end latency of 3 to 7 seconds, this might be the solution. But what needs to be understood in doing so is that there are a few caveats. And one is that we've seen that behavior of such system is greatly affected by client implementations. Some clients are more robust than the other. We also seen that even with robust clients, the number of buffering events is higher than what it should be. For T-Mobile, for example, the number of buffering even for AVPlayer was greater than 1, and same for DASH.js. We also noticed that, especially for low latency HLS, the number of requests that are going to CDN and the origin server is much higher. That has to have an impact on scalability and on delivery costs. And importantly, what is getting affected is consistency of experience. There is much more switches that can be expected with low latency systems as opposed to non-low latency systems. And that number of switches between different streams might just have detrimental impact on quality of experience. Same as the variation of latency. Some people just might get surprised that, how all of a sudden, in the middle of my football game now, I'm a few minutes behind as opposed to my neighbor. But good news is that all these things that we observed, they seem to be just side effects of the fact that these are still fairly young and not finely tuned yet designs, and there is still much more work is possible on improving streaming client algorithms. In fact, every year at ICN Multimedia, we see new algorithms being proposed. This year, we've got a few more algorithms that's been proposed. We just finished studying 2 that were proposed last year. Now we need to do it, work all over again to study new ones. But eventually, we believe that all those questions could be addressed, and we'll have much more robust and reliable low latency streaming ahead of us. With this, thank you very much, and thank you for tuning in, and enjoy the rest of the conference.
Hey everyone, I'm back and I'm here with Yuriy Reznik. Thanks, Yuriy.
My pleasure. Thank you for inviting me to talk at the conference, and I'm happy to answer any questions.
Absolutely. Yeah, I think I can speak for most of us here watching when I get to that. Live streaming latency is a huge topic consideration, and one that's increasingly growing with the rise of interactive live video experiences in the market. So thanks again for sharing all your learnings and experiences. So with that, switch over to the audience Q&A again, and a reminder to all attendees that you can ask your questions in the live comments, and we're doing our best to answer them in line and also ask some of them live here. So the first one, just kind of a general question, kind of really not for you, Yuriy, maybe for me or the organizers, but the question is, where can I find these slides? Maybe if you missed the beginning or if you were having trouble hearing part of it. The answer is we'll be posting the recording of this and all talks on the Facebook page after each day of the conference. So don't worry if you miss anything, it'll all be there for you to watch later. Now, the first question for you, Yuriy, was really about it seems like it's about the delay calculations you're using. It says 10 or
Mhm.
30-second delays. What do you mean? Is that time to first frame, or is that time from upload to availability? So could you expand a little bit on how you measure latency?
It is basically glass-to-glass latency. You start with live event and time of capturing content to the time of delivery. As you all know, in broadcast, the rule of thumb is that delay should be about 5 seconds or less. Of course, with traditional streaming, it is much larger. And idealistically, if we set up things right with low latency streaming systems, we should be able to achieve much lower delays. And that's what our experiments have confirmed.
Makes sense, makes sense. So the next question is about how do you ensure the latency is lower than the segment size? Since you have to begin playback at a keyframe, those are usually the segment boundaries. So do you, for example, wait for the next segment, or what kind of strategies do you employ there to ensure low latency?
Well, in this case, it sounds like I didn't do a good job explaining how low latency streaming systems work, so my apologies for this. So this low latency streaming system, it's the same mechanics as with traditional streaming. You still encode video with gaps, with periodic insertion of IDR frames, and but this traditional streaming, we used to have longer segments. The segments, in, for example, an original HLS was about 10 seconds, and this low latency streaming, you could chop this 10 seconds in 10 chunks, and you still would encode them with shorter gap size. So there is a keyframes inserted at the boundaries, and then you just send those shorter subsegments or chunks. And there is a difference between low latency HLS and low latency DASH. With DASH, you use so-called chunk-based transfer, where you initiate transfer once, and using HTTP 1.1 chunk transfer, that entire segment is being delivered incrementally. With HLS, each of these subsegments being announced as an independent entity and being pulled separately. This is why we have higher number of requests with low latency HLS streaming systems. But otherwise, you still have gaps same way as earlier. I hope this makes sense.
I hope that answered the question for the viewer. Another one here. So this is a little bit more open-ended, Yuriy. What strides are being made in near real-time latency streaming at scale, and specifically with what technologies?
Well, it is a fantastic question. And there is actually a combination of different competing technologies nowadays that being suggested for near real-time streaming. If we're talking about low latency streaming, it's still built based on HTTP-based protocols, and we're talking about reducing latencies from tens of seconds down to a few seconds, like 3 to 5 seconds, 7 seconds is what we've seen realistic. This low latency varieties of HTTP-based streaming protocols. If you want to go to even lower latencies, there is no way around of transmitting things frame by frame, and at that point we will be talking about stacks like WebRTC or stacks used for video conferencing effectively since H.261 and T120. If you go back or create compression labs and picture. So basically, if you want to go down to milliseconds, that's where you will need to send things frame by frame, and of course you probably will need to use UDP at that point, or use protocols that don't require guaranteed transmissions, so there is no round-trip delays, retransmissions attempts, and so on. So that's life of real time.
Yeah, that makes a lot of sense. And I guess going from that to now maybe a question about the client, and this is, I think, our last question for you. it's another open-ended one. How do you envision the state of the art for client streaming might look in 30 years or so?
Well, it depends which protocols clients will still be using. What I could certainly say is that we've seen remarkable progress in designing of low latency streaming clients in the last few years. In fact, by the way, I misspoke. It's not ACM Multimedia, it's ACM Multimedia Systems Conference, very prominent event that happens every year. And every year at this conference, we see several new algorithms being proposed for low latency HTTP-based streaming. So the two algorithms we studied here were LOL and L2O. Well, there is now LOL plus. There are a few other algorithms that's been proposed recently at the same conference, and actually other sources. And so the field is very rapidly moving. There are improvements. There is extensive use of AI, ML types of techniques and designing of these algorithms. So if clients stay with HTTP-based concept where all adaptation and intelligence, so to speak, sits at the client side, the clients will get more and more sophisticated. There's no other way around it. And of course, if protocols will change, if we'll go back to UDP for some use cases, well, then maybe for those clients, the architectures will be different and the decisions will be different. It might be distributed logic, some more things done on the server side.
True. Very good answer. I think that's the last question we had. Did you have any closing thoughts, Yuriy, or did you cover most of what you wanted to say?
Well, I would like to thank everyone for listening. Thank you for the invitation to talk at this event. It's my pleasure. And thanks, everyone, and enjoy the rest of the conference.
Of course. Nice to meet you, Yuriy.
My pleasure.
Next, I'd like to introduce Justin from iStream Planet, who's going to be talking about how they built high availability live encoding